What is a dataset? 3 words that contain the entire foundation of artificial intelligence. Every model you have ever used, ChatGPT, Google Photos, fraud detection at your bank, all of them started with a dataset. By the end of this video, you will know exactly what a dataset is, how it is structured, why quality matters more than size, and how data flows from raw collection to a trained model. No jargon. No shortcuts. Let us build it from scratch. A dataset is a structured collection of examples that a machine learning model learns from. Think of it like a spreadsheet. Every row is one example, one observation. Each column is a feature, a measurable property of that example. Take a house price dataset. One row is one house. The columns describe it: size in square feet, number of bedrooms, location, age of the building. One special column is the target, the thing you want the model to predict. In this case, the price. The model's job is to study thousands of these rows and learn the mapping. Given these features, what is the price? Features are called X. The target is called Y. The model learns the function from X to Y. Not all datasets are the same. There are 2 critical splits you need to understand. Split 1, does the data have answers? If every example comes with the correct answer already attached, like an email labeled spam or not spam, or a photo labeled cat or dog, that is a labeled dataset. If the data has no answers attached, just raw examples with no predefined categories, it is unlabeled. Labeled data enables supervised learning. Teach the model by showing it thousands of correct examples. Unlabeled data is used for unsupervised learning. Find hidden patterns, clusters, and structures without being told the right answer. Split 2, what is the data format? Structured data fits in rows and columns, spreadsheets, SQL tables. This is classical machine learning territory. Unstructured data has no fixed schema: images, audio, video, raw text. This is deep learning territory. Before you touch a model, you must divide your dataset into 3 parts. The training set is the largest, typically 70%. This is the data the model trains on. It sees these examples and adjusts its weights. The validation set, around 15%, is used during training to check whether the model is overfitting. Overfitting means the model memorizes the training data instead of learning general patterns. If training accuracy is high but validation accuracy is low, you are overfitting. The test set, the final 15%, is held completely separate. The model never sees it during training. You only use it once, at the very end, to report the final unbiased accuracy. Think of it like school exams. Training data is the textbook you study. Validation is the mock exam that guides your revision. The test set is the real exam, you get one shot. Never let your model peek at test data early. That is data leakage, and it will give you false confidence. Here is the most important lesson in all of machine learning: garbage in, garbage out. A model is only as good as the data it trains on. Bad data produces bad predictions, guaranteed, no matter how sophisticated your algorithm. The most common data quality problems are missing values, rows where some columns are empty. Outliers, values that are impossibly large or clearly wrong, like 999 bedrooms. Inconsistent formatting, the same location written as Zone A, and Zone A duplicate rows, the same example counted multiple times. And wrong labels, examples tagged with the incorrect answer. Before training any model, you must audit and clean your dataset. Handle missing values by filling them with the column average, interpolating, or dropping the row if there are too few missing values. Remove or cap outliers after investigating whether they are genuine extreme cases or data entry errors. Standardize all categorical values to a consistent format. Here is the harsh reality: machine learning engineers spend approximately 80% of their time preparing and cleaning data, and only 20% building models. 2 questions every practitioner asks: how much data do I need? And is my data representative? The answer to the first depends on the algorithm. A logistic regression can work with a few hundred rows. A random forest needs thousands. A neural network typically wants tens of thousands. A large language model like GPT requires hundreds of billions of tokens. But more data is not automatically better. There are diminishing returns. Doubling your dataset rarely doubles your accuracy. Quality beats quantity every time. The second question, is your data representative, is even more important. Dataset bias means your training data does not represent the real world your model will face in production. If you train a credit scoring model on historical data that reflects past human biases, the model learns and amplifies those biases. If you train a face recognition system only on images of light-skinned people, it will perform poorly on everyone else. Bias in data leads to unfair, unreliable, and sometimes harmful models. It is not just an ethical issue, it is a technical one. Some datasets have shaped the entire trajectory of artificial intelligence. NIST, created in 1998, contains 70,000 images of handwritten digits from 0 to 9. It became the hello world of deep learning, the first dataset most researchers test a new model on. ImageNet, assembled in 2010, contains 14 million labeled images across 1,000 categories. In 2012, a deep neural network called AlexNet achieved 96% accuracy on ImageNet, demolishing the previous record held by classical computer vision. That single benchmark result triggered the modern deep learning revolution. Every company poured resources into deep learning because of one dataset. Common Crawl is an ongoing project that scrapes the open web and stores the raw text. It is now measured in petabytes. GPT, BERT, Llama, virtually every large language model trains on Common Crawl text. One dataset shaped vision. One shaped language. The data defined the direction. Raw data is rarely ready for a model. First, you must transform it into meaningful features. Feature engineering is the process of creating new, more informative columns from your raw data. Take a fraud detection dataset. The raw columns might include a raw timestamp, a transaction amount, a merchant identifier, a device ID, and an IP address. These raw values are low signal. A timestamp alone tells the model nothing useful. But if you engineer new features from them, the hour of day, flagging 3 a.m. as suspicious, a log-scaled amount, a merchant risk score based on historical fraud rates, whether the device has been seen before, and the number of transactions per minute from this IP, now the model has actionable signal. This is the difference between a raw event log and a well-prepared feature matrix. For classical machine learning, feature engineering is a critical manual step. Domain experts who understand the problem design the features. Deep learning reduces, but does not eliminate, the need for feature engineering, because neural networks can learn some feature representations automatically from raw inputs. In production, a dataset is never a static file you download once. Data pipelines continuously collect, process, and update the data that feeds your models. The pipeline has 4 stages. First, collection. Data arrives from databases, APIs, IoT sensors, user events, web scrapes. Second, cleaning. Automated scripts handle missing values, standardize formats, remove duplicates, and flag anomalies. Third, feature engineering. Transforms are applied consistently. The same transforms used at training time must be applied at inference time. If they differ, your model breaks silently in production. This is called training serving skew, and it is one of the most common production failures. Fourth, splitting. The cleaned, engineered dataset is split into training, validation, and test sets. Then training begins. 2 other critical risks: data drift, when the real-world distribution shifts over time, making your training data stale. And pipeline leakage, when future information accidentally enters past features, making your training accuracy look great but your production accuracy collapse. So here is the complete picture. A dataset is a structured table of examples. Rows are samples. Columns are features. One column is the target. Labeled datasets enable supervised learning. Unlabeled datasets enable unsupervised learning. Always split before training, 70% training, 15 validation, 15 test. Never peak at the test set. Quality beats quantity. Clean, unbiased data trains better models than large dirty datasets. Feature engineering transforms raw columns into predictive signal. It is both an art and a science. The full pipeline is collect, clean, engineer features, split, then train. And remember, the data defines the AI. Not the algorithm. Not the compute. The data. If you want to go deeper, how to handle class imbalance, how to build a feature store, how to detect and fix data drift, subscribe. Every week we go this deep.